Today we're going to test a diode and with a function generator and an oscilloscope. Now there's other things that might be better for this called source measurement units, but they can be expensive, and in a lab situation I can't put one at every station. So what we're going to do is sweep a voltage across an R diode connected circuit, and notice it's going to start at zero point 0.1 volts and go up to 10. And then what we'll do is when we measure it, we'll find the current by taking the difference in these two voltages and dividing by the resistance. And then we'll get the actual diode voltage will be the x-axis. So when you can download this circuit, again, that's to help you. But you shouldn't use it in your report. You should use your own group's image, although I recommend using your own. So when you run it, you see a diode curve, and then I've taken the logarithmic natural log of that, and notice I get a straight line. Well, I can use that straight line to extract the ideality factor and the reverse saturation current. And the things that you need is the slope and a XY pair. It can be the first one or the second one. But when you're doing this, make sure that you're doing it in a linear spot. I've kind of made it so that it should be linear everywhere. But notice how the slope goes to 22. If I go the whole range, oops, okay. And I just happen to know that that up here we're starting to see the series resistance effect. I can't really measure the series resistance in this setup because the amount of current flowing through that diode will ultimately blow it. And so we'll just read off the RS value from the diode. Now, what does LT Spice use for ideality factor? So if I right click on the diode, pick new diode, might be hard to see, but the reverse saturation current, the series resistance, and the ideality factor, plus some transient parameters are all there. Okay. If you've somewhat forgotten how to extract that, I do have a link in the lab manual to some notes, but I even kind of give a quick derivation of kind of what you're doing. All right, so to give you a quick hint. All right. So once you've done with that, all right, the next thing will be to build this circuit and put in the IO you measured, the RS you measured, or actually the RS you have to get from the parameter file. It's 0.65. It's in the manual. And run it, and then you're going to compare this current to that current, and it should be pretty close. All right. Then the next step you're going to do is you're actually going to measure it. Okay. And that's step 5. The code is here. And notice if you use a different resistor or you go and calibrate it, change it in line 112. All right. And what I mean is if you look at what I did, this is my picture. I didn't have a 500 ohm resistor, but I had two 1K. I just tied it together. But I could actually then measure the resistance here and then use that in my code rather than just what rather than just what the markings tell me. Then I would have a more more accurate measurement. All right. So when you run the code, you should get something that looks like that. And then you open up the file in Excel. Remember that file, that program will save the file as Excel. I've called it diode. And then what you do is you wait, you look at where it's positive, and then you take the natural logarithm of the current, and then you plot the diode current and the diode voltage, which happens to be, or the log of the diode voltage. So you plot V out, which is the diode voltage, and the log of the current, and then you can just click on it and do linear display equation display R, and it gives you the slope and the intercept right away. Here I use the whole data set and I got an N and an IO. Here I kind of zoomed in on a more, looked like it's better, and I got 1.91 and 12 nanoamps. This one seems to match better, and so maybe that's how they extracted it. But this the R squared is a lot closer to 1, or it's closer to 1 than that. All right. And so that's really it.